Yesterday presented a presentation on similar topic. Hope that I am different from what he presented. So what we are going to discuss. I have given 13 points, and some of the points I will leave if the time is not more than 1 hour 30 minutes. First, I will briefly list the natural and man-made disasters, and then we will talk about progressive collapse and structural integrity, and then seismic damage to structures and seismic design of buildings. And in that, detailing is as important as design. And some of the seismic moment connections in steel structures which have been developed in the USA, and what is meant by robustness and resilience in structures, and then about resilient designs and increasing robustness of buildings using base isolation, energy absorbing devices, and also simple method of increasing robustness. And then the foundation design, this from 9 to 13, I will skip if the time is more than 1 hour 30 minutes. Then wind induced failures, mitigation of wind induced vibration of tall buildings, fire resistant design of structures, and preventing terrorist attacks on tall buildings. So, coming to the list of natural disasters, there are several disasters. They can be classified into geological disasters, hydrological disasters, meteorological disasters, and climatical disasters, which are concerned with our we us, that is structural engineers. There are also biological disasters and space related disasters, which we will not discuss. And out of this, for landslides, there is a new code, IS 14680, which was released in 2024. And tsunamis, it is very difficult to design. And there are two documents. They are ASE 722 and FEMA P646. They, of course, they give some information about how to design for tsunamis. Of course, floods and droughts, storm surges are hydrological disasters, and meteorological or wind, which can be in the form of cyclones, hurricanes, and tornadoes. And there can also be snowstorms, heat, cold waves, etc. Climatical disasters are wind fires and glacial retreat, etc. I have given only a few examples. And there are so many human-made disasters. It can be industrial disasters, structural failures, fires and explosions, environmental disasters, wars and terrorist attacks, cyber disasters, transportation disasters, public health crisis, etc. So I have also given some of the examples here. Bhopal gas tragedy, Chernobyl disaster in 1986, and Fukushima 2011 in Japan. And then buildings or bridge or dam failures are examples of structural failures. Of course, wildfires you have seen recently. There was havoc in San Francisco, and oil spills, deforestation, plastic pollution, etc., which we are not going to discuss. So, as I already informed, climate change is a very great human-made disaster. As per United Nations Office for Disaster Risk Reduction, economic losses have quadrupled over the past 50 years due to urbanization and climate change. So, climate change results in more frequent and intense natural disasters. It is leading to frequent and intense hurricanes, wildfires, and earthquakes. Of course, with earthquakes, I cannot say, but they say that it can also induce earthquake, which can damage and destroy structures. And it will result in increased flooding due to cloud bursts and sea level rise. Of course, we are seeing even in Chennai, 1 month rain is coming in 1 hour. And there can be changes in temperature and precipitation patterns, resulting in fires like the current LA fire. And it can also lead to soil instability and landslides, which can damage foundations and structures. And also, it can result in increased risk of corrosion and deterioration. So some of the key tools to tackle climate change are building information modeling, computational fluid dynamics, geographic information systems, and sustainability and resilience rating systems. These rating systems, such as LEAD and Envision, provide frameworks for evaluating the sustainability and resilience of structures. According to the World Bank, natural disasters cost the global economy 250 to 300 billion dollars annually. So now let us go to the progressive collapse and structural integrity. Building regulations all over the world address robustness issues. That is why I have included this as a first slide in the presentation. In the design of tall and large occupancy buildings following the Ronan Point incident in 1968. This is a 22-story apartment block in East London, and it was constructed using prefab concrete panels. So you see that there is a partial collapse of one corner triggered by gas explosion on the 18th floor and demolished a load-bearing wall over nearly its entire height. 4 people were killed and 17 were injured. It resulted in progressive collapse provisions in the British Code in the 1970s. So these are the structural integrity things, clauses introduced in BS 5950. That is, we have to tie all the columns with internal ties and vertical ties. Of course, you may be happy to note that structural integrity criteria are being introduced in the fifth revision of IS 4456 in class 9.7. So it is very important to tie all columns in all directions to achieve structural integrity. So let me go to seismic damage to structures. You all already know that earthquakes do not kill people, but improper design and detailing do. So this shows the collapse of a partially open ground floor building in Butch earthquake. You see that it not only collapsed, there was a vertical split at the middle. What are the factors that influence the seismic damage? Peak ground acceleration, amplitude, duration and frequency of ground vibration, magnitude of earthquake, distance between epicenter and site, geographical conditions, soil properties at the site, and foundation type. Of course, building type and characteristics will also result in damage. This shows a damage to a steel building in Mexico City earthquake in 1985. So the major recent earthquake in India was was the Bhuj earthquake in Gujarat, which was on January 26, 2001. It was a M7.7 earthquake. It killed 20,000 people, injured 167,000, and destroyed 340,000 buildings. And property damage was estimated as 4,519 million rupees. So this shows the collapse of 5-story buildings, collapse due to soft story effects. This shows the short column effect of a warehouse in the port of Kandla. So their observations in several past earthquakes indicated very poor performance of buildings due to several reasons. So those reasons are shear critical columns, weak columns and strong beams, sudden change in stiffness, soft story, plan and vertical irregularity, torsional irregularity, unconfined beam column joints, weak stories, floating columns, etc. So I have shown some of these failures here. This is shear critical column, plan irregularity, open ground floor failure, that is soft column, soft story, and this is torsional irregularity because of a L-shaped building. And several failures of columns were also observed due to buckling of column reinforcement. This is an example. Due to insufficient lateral ties and insufficient transverse reinforcement in beam column joints, poor anchorage of beam bars in beam column joints, provision of strong beams and weak columns, and improper detailing in plastic hinge zones. There can also be punching failures, and these are some of these are complete collapse due to improper detailing in plastic hinge zones. I wanted to show this interesting slide, which shows the column failure in the same building during 1971 San Francisco earthquake. This shows the failure of the building. Uh, there was a 600 drift in the first story. You see that this rectangular column failed completely, and you don't see any lateral ties, whereas this spirally reinforced column in the same story still carrying load because of the spiral reinforcement, which are closely spaced. Of course, there can be other failures. Pounding, soft story I already explained. This shows the example of failure of the column, and we can there can also be collapse of water tank. So, in IS 1893, it says that vertical and horizontal projections should be designed for 5 times the design horizontal acceleration coefficient, because these cantilever structures are bound to fail if it is not properly designed. So let us go to the next section, seismic design of buildings. And we have a lot of codes, and they are being reviewed or revised quite often. This is IS 1893. It was revised in 2016, and there is already a draft code. And IS 13920, IS 18168. This is for steel buildings, and then IS 4326, which was released in 2013. So let me show you the lateral force resisting systems in concrete, shear frames, moment resistant frames, brace frame. Of course, you know already all this. And buildings with a regular configuration steel, once again with the shear walls, braced frames, moment resisting frames. So the architects play a bigger role in having structures which perform better in earthquakes. So we should have simple and regular plans in order to have better performance. Uh, so rectangular buildings are good, better are square, and best is a circular building. But we don't always uh, use a circular building because of some other problems. And this is very bad because the length is very large compared to the breadth. And worst are T shaped building or L shaped building, because there can be damage at the re-entrant corners. So planning is very important. Of course, it is not in the hands of structural engineers. The effect of asymmetry will induce torsional oscillation structures and stress concentrations at re-entrant corners, as I told you in the previous slide. And all the irregularities that are mentioned in class 7.1 of IS 1893 are to be avoided. There can be planned irregularities or vertical irregularities. Of course, most of you may know all this. So I am not going into that, but I have listed some of these planned irregularities and vertical irregularities. So a building with the irregular configuration, T-shaped, L-shaped, U-shaped, or cruciform in plan, and other complex shapes should be avoided. And setbacks and multiple towers, of course, IS class 8.1.3.3 of IS 16700, that is for multi-story buildings, gives some more discussions on multiple towers like this and backstay effects. And then split levels and unusually high story, or unusually low story, or the outwardly uniform appearance, but the masses are not symmetrically placed. All these things should be avoided. And buildings with abrupt changes should also be avoided. So soft lower levels, of course, this is very bad. In most of the metropolis, we see buildings with lower, soft lower levels in order to have car parks, but they have to be properly designed, or we should have some shear walls in the ground floor so that the stiffness is not varied. Large openings in shear walls, interruption of columns, interruption of beams, openings in diaphragms, interruption of vertical resisting elements, abrupt change in size of members, drastic changes in mass and stiffness ratio. All these things should be avoided in order to have proper uh, earthquake resistance. Can we design to resist earthquake with no damage? Yes, of course. We can design structures to resist catastrophic earthquake with no damage at all. However, it will be prohibitively expensive and unwarranted for the small probabilities of occurrence of such catastrophic earthquakes. Instead, the objective is to reduce the probabilities of fatalities to an approximately small value. So so that is why the earthquake design philosophy that is given in IS 1893 is minor and frequent earthquakes should not cause any damage to the structure. So like this, and moderate earthquakes should not cause significant damage but could have some non-structural damage. Major and infrequent earthquakes should not cause collapse. So it can have damage but should not collapse. Hence, design is done for much smaller forces than actual seismic loads. So this approach is different from the case of wind, dead, live load, and other loads, where the structure is designed for the actual loads. Actually, it is important to note that till now it is not possible to predict where an earthquake will strike, and also its magnitude or intensity or any other feature of the earthquake. So we are reducing the actual forces by using a response reduction factor, or of course the name has been changed in the draft course. So the how will the structure will not collapse? It is due to the overstrength, redundancy, and ductility. So they are shown here. So we are designing for this force, but the actual force is largely higher. This is very important actually in earthquake resistant structures. Many people don't follow this, but total drift is very important. It is as per IS 16700. Total drift at the topmost usable floor should be limited to h by 500, and in single story, the drift may be relaxed to height of the story by 400. For design earthquake force, the maximum interstory drift shall be height of the floor by 250. And one of the things that is advocated in our course is that we should have a strong column and weak beam, and the reverse should not be used. That is weak column and strong beams. It is because if you have uh, such a thing, that is strong column, weak beam, you will have this kind of mechanism where the plastic hinges will form in the beams, and only at the end the plastic hinges will form at the column. This will that's why this concept will make plastic hinges to form in beams only. So detailing is as important as design. It is shown beautifully in this figure, which was taken from Poultry and Legeron in 2008. So you see that if the lateral ties are uh, very largely spaced, we do not have confinement of concrete, whereas if you have closely spaced ties, the confinement of concrete is very high, and the longitudinal reinforcement work together effectively under compressive loads, increasing the column strength, ductility, and overall structural performance. And it is also important to have 135-degree hooks in earthquake zones. And when you have short columns, the entire length of the column should be reinforced with closely spaced ties. Of course, this is also not followed in most of the buildings. Detailing of beam column joints, because it is very difficult to place ties in the beam column joint, but it is important not only to have the lateral ties in the beam column joint, but also to have 135-degree hooks that resist the ill effects of the distortion of joints. And it is also important to have equally distributed shear walls in all the directions, so that we will have the desired performance. The shear walls should also be detailed properly. It is important to have closely spaced transverse reinforcement in wall boundaries. I have shown here, and we should also have closely spaced reinforcement here. And this shows a wall failure in the 2011 Christchurch earthquake in New Zealand. Of course, it is better to have coupling beams instead of full shear walls. And this is a detailing which was researched by Professor A.R. Santakumar of the Anna University when he was working with Professor Pauly of the New Zealand. And now this kind of reinforcement, this was the normal reinforcement which was used previously, and this is the reinforcement which is used now. And most of the courts, they follow this reinforcement now. And this shows a failure of the conventional detailing. This is the 14-story street apartment building in the 1964 Alaska earthquake. You see the failure in the coupling beams. So let me go to the seismic moment connections in steel structures. So in order to avoid failure, the following three strategies are adopted usually. That is toughened connections, strengthened connections, and weakened connections. Actually, IS 35822 is an AAC code. Sorry, AAC code. AAC 35822. It gives pre-qualified connections for steel special moment frames for seismic applications. It gives the details of several these 12 connections which have been tested adequately, so that it will resist earthquake forces. So these are strengthened connections. So using cover plates, using ribs, using side plates, and using haunches. The aim is to ensure plastic hinge locations at distance of half the beam depth from the column face. So because in order to avoid the plastic hinge location at the joints, which are very important. There is also an important and interesting connection. It is called as Kaiser bolted bracket moment connection. This consists of a cast steel bracket, which is not mild steel, but it's a cast steel bracket, which moves the plastic hinge location at this from the joint to this location. So this shows the actual joint, and this shows the structure in which it is placed. Of course, first thing which was developed was dog bone weakened connection. That is, it is also called as reduced beam section. So once again, the idea is to move the plastic hinge location from the joint to away from the joint. So this is the reduced beam section. It is shown. There is an arc cut. So the radius of the cut is shown here. And this can be straight or tapered also. And some people have researched having constant hole diameters or increasing hole diameters. And this shows the relative cost of the joint. Of course, 1.0 is the normal welded flange bolted web. which was adopted pre Northridge earthquake. So this one is increases the cost by 1.771 times, and there are other. Of course, I have shown in the previous time cover plate, etc. They increase the cost by 2.5 because we need extra fabrication, and side plates increase by 3.96, and top and bottom haunch increase the cost by 4 times. This is a patented connection which is called the side plate connection. It you see, as I showed in a previous slide, it consists of lot of extra plates near the joint, so that the plastic hinge location is placed away from the joint. So now we will go to robustness and resilience as applicable to structures. Robustness is defined as the ability of a structure to withstand events like earthquake, wind, etc. without being damaged, whereas resilience refers to the capacity to recover and return to full function after experiencing damage from an extreme event, focusing on the ability to bounce back after disruption. Thus, robustness is about preventing significant damage in the first place, while resilience is about recovering from that damage quickly. So, schematically, it is given like this. So, this is damage and it is bounced back. So, you may be interested to know that structural robustness criteria, that is resistant against fire, blast, and impact, are introduced in the 5th revision of IS 456. So the key differences between robustness and resilience are focus on damage. Robustness prioritizes minimizing the extent of damage caused by an event, while resilience focuses on speed and effectiveness of recovery after damage occurs. Robustness is considered proactive approach, designing structures to withstand extreme loads from the outset, whereas resilience involves considering recovery strategies after an earthquake has happened. The examples are, in robust design, a building with redundant structural elements and strong connections to prevent localized collapse in case of an earthquake, whereas resilience design, a building with easily replaceable components and rapid repair mechanism to quickly resume function after an earthquake or natural disaster. I wanted to show this slide of a resilient structure, which is the Empire State Building, which is a new 100-story building, which is 443.2 meters tall, which was the highest building in 1970, and it was designed by Shreve, Lamb, and Harman, and it was built during 1930 to 31 when there was no computer or computer software. It was considered as one of the 7 wonders of the modern world by the AICE. On July 28, 1945, a B-25 missile bomber fell into the north side between the 79th and 81st floor, and the building survived the impact. Since 2011, it is powered by 100% renewable wind energy, and it is aiming to achieve carbon neutrality by the year 2030. So let us see what is meant by resilient designs. The code required minimum design for earthquake resistance is based on balancing economy and life safety that I told you already. Structural engineers designed lateral systems with certain components intended to absorb earthquake energy through inelastic response to prevent collapse. Let us compare the number of fatalities between 2020, that is M7 Haiti earthquake, and 2011 New Zealand Christchurch earthquake. So during Haiti earthquake, 200,000 people died. In the 2011 New Zealand earthquake, only 185 people died. Clearly, the ductility-based seismic design enforced by code standards and other things is successful at providing life safety. But in Christchurch Central Business District alone, more than 1,400 buildings were demolished. At the time of the earthquake, the population of the Christchurch was only 350,000. Think about the damage in larger cities like San Francisco, Los Angeles, or even New Delhi. The number of buildings that would be damaged and then require either very long and costly repair or demolition would be much greater. So the structural engineers should initiate discussions related to the functional recovery objectives early in the design process. They should clearly communicate to the owners that meeting a code minimum will result in damage that could require repairs that render the building partially or completely unoccupiable for months or even years following the event. The functional recovery objectives are critical in selecting the lateral and gravity systems. Different lateral systems, as you know already, shear walls, braced frames, moment frames have different functional recovery characteristics. Shear walls and braced frames tend to have lower relative story stiffs, but also may have higher floor acceleration. Moment frames tend to have higher relative story stiffs, but lower floor accelerations. Both structural and non-structural damage are affected by the dynamic characteristic of the lateral systems. Very stringent functional recovery objectives may require the use of seismic isolation or supplemental viscous dampers, which we will discuss later. So, how to select the lateral system? High ductility systems will incur significant damage in a design level or greater earthquake. The building code, such as IBC and AAC 7, provisions that improve functional recovery require designing for higher forces and decreasing allowable drift limits. As I told you, the drift limit is very important. These requirements improve functional recovery, but they have cost implications. So this cost is again and again. I am telling that cost will increase if you have less damage. If you want to have less damage, strength and stiffness are two controls that structural engineers have that could affect functional recovery, but they are not the only controls available. Let us see how. This is a example. The damage comparison between RC shear wall and coupled shear wall. So when you have shear wall, the failure will be here, flexural and shear yielding at the base of the wall. Whereas in a coupled shear wall, the damage will be in the coupling beams. So typical reinforced concrete wall designed to yield at the base of the wall, which can be very difficult to repair. Whereas coupling beams are slightly better to repair. So after a significant event, these coupling beams can be repaired easily. So another way is to have a replaceable fuse. Replaceable fuses are designed to absorb earthquake energy in a component that is easily repaired or replaced. So let us see this. This is a steel moment resistant frame. So as we have seen, plastic hinges will form in the beams at the two ends. Whereas if you have a replaceable fuse plate, damage will be here only. So which can be easily replaced. So we will see an actual system that has been developed and also presented in the AAC 358 22 edition of the code. This is called Durafuse moment connection. Of course, there are different figures. This shows one-sided Durafuse connection with wide flange columns and beams. So you see that there are a lot of plates, and there is also a plate here. This is called as a fuse plate. So the connection has a steel fuse plate at the beam bottom flange that limits the amount of force that can develop at the face of the column. The shear yielding mechanism in the fuse is not susceptible to local buckling, so large rotations can be accommodated without strength degradation. This patterned connection, of course, I already explained this. And there are other details which are provided in the AAC 358. Four external continuity plates that extend past the face of the column are fillet welded to the column cover plate. The column has a single plate shear connection with horizontal starter holes. and the beam web with standard holes is attached to the single plate shear connection with pre-tensioned bolts. So you may refer for the equations and also more details in the AAC 358. I think all AAC codes can be downloaded free. So now we will see what are the modifications that are required in braced steel frames. So if concentrically braced steel frames, the area shown in red will be damaged during earthquake. Gusset plates damage due to brace buckling, and steel brace yields in tension and buckles in compression in these areas. Whereas if you have a buckling restrained braced steel frame, buckling restrained steel frame yields in tension and compression in these points, but this can be easily replaced. The damage is confined to the buckling restraint BRBs, which can be replaced following a significant seismic event. Another thing which has been developed is the controlled rocking braced steel frame. In the rocking braced frame is a unique lateral system in which the brace frame is allowed to rock at the foundation level. At this level, it is allowed to rock. The frame shown here also has the advantage of being able to self-center because of this high-strength cable. The frame recenters itself using a tensioned high-strength steel cable. And RBF is likely to increase the initial frame cost but benefits to functional recovery after an earthquake. It would more than offset the upfront cost. The damage is absorbed in the yielding fuses on either side of the frame, which are designed to be easily replaceable. So there are several examples of resilient components that have been developed and adopted in New Zealand. They are replaceable frame shear links like this, pre-thrust ring feeder hold down springs like this, and the key difference is the resilient components as above are integrated as an accessible replaceable component with sufficient ductility to dissipate seismic energy. Of course, I will show another few more examples in the next slide. Compression and tension yielding buckling restraint braces, which we already discussed, and then compression and tension yielding energy dissipators like this, sliding friction joints, these are examples, and lead rubber base isolation bearings and concave friction sliding base isolation. Of course, they have calculated the cost and they found that the cost premium for resilient building design is typically 1 to 3% of the total construction cost. With base isolation is slightly expensive, that is 5 to 7% of the total construction cost. Of course, I forgot to tell you that I have given at the end the references which you can go through later. So some more components. This is U-shaped flexural plate, which is also useful in resisting the earthquake and is easily replaceable. And energy dissipating steel plate connector. It is shown here. We will see some of the examples of buildings in which these components have been used. So this is a super lot 7 building in Christchurch. This is a precast concrete walled building with ductile weld plate connectors, which I have shown in the previous slide. The plates can be accessed and replaced if necessary, and they are hidden from the view. All the precast walls in the longitudinal direction were detailed to allow for ductile response at the base. So this is the building as required by a coupled wall system by a long debonded length of starter bars connecting the panels to the foundation. Hysteric energy is dissipated by plate yielding like this. The plates acting as yielding fuse. Each connector is welded to the cast in plates. Another example, This is a rocking, concentrically braced frame. I have shown this detail earlier also of the D. Pune Student Accommodation Building in New Zealand. This is an award-winning building in Wellington, New Zealand, and a rock which has a rocking concentrically braced frame with ring feeder hold down springs. The springs dissipate energy through the rings with a conical interface. Actually, the springs have pre-compression applied to counter uplift forces due to seismic actions. In some cases, additional post-tensioning can also be applied to supplement the spring compression. This is the component which has been developed and used. This is a pole tension rocking wall structure for NMIT, New Zealand. This is an award-winning building built in 2009. This is a timber multi-level post-tension rocking wall structure combined with U-shaped flexural plate. I showed you the U-shaped flexural plate in a previous slide. So the same building, these are also called as the plug and play dissipators. They are mild steel bars with yield both in tension and compression. They are inside this. The bars are confined by steel tubes filled with grout and epoxy. This is a tube, and the bar is inside. The dissipators activate with the opening of a gap and are typically used in rocking structural system providing ductility. The yielding and plastic straining is concentrated over a defined length. Of course, it is inside this tube, defined length through the use of a reduced steel area. So similar to the reduced beam, here also there is a reduced steel area of the bar. Another interesting thing, this is a two-way sliding hinge joint of the terrace stage Christchurch. This shows the building, and this shows the joint, and this is an important thing which shows the operation of this mechanism. So using this plastic two-way sliding hinge joint, the seismic energy is dissipated by controlled sliding of tensioned steel plates with minimum damage to the structure. It is so designed that the beam is pinned. You just see here. It is pinned to the column at the top flange level and is connected at the bottom flange and the bottom of the web by unique asymmetrical friction sliding detail. This is the friction sliding detail which functions via rotation generated by seismic moments. When the rotation will happen here due to this hinge joint. The SSJ dissipates energy by opening and closing each time pivoting about the top flange connection. These are rigid under working load, slide under design level earthquake, and return to rigid connection at the end of the earthquake shaking. These bolts and friction plates could be replaced as needed because they are only joints here and here. They can be replaced very easily. So after discussing about the resilience, let us go and discuss about the robustness of the buildings. So one such technique is the base isolation technique. Uh, it is one of the most significant development in earthquake engineering in the past 35 years. So you see that these are the isolation bearings, and you can also have another passive damper. So during the earthquake, only the isolation bearing moves, and the loads on the structure is considerably reduced. It provides the design profession the ability to design a building that is operational after a major earthquake. So let us check how these base isolated buildings performed during previous earthquake. So William Clayton Building in New Zealand is the world's first base isolated building. And in India, the 300-bed district hospital in Bhuj after the January 2002 Bhuj earthquake, it has 280 lead, rubber, and sliding bearings. and isolators of up to 1600 millimeter diameter and about 600 millimeter height are currently available. This size is capable of sustaining over 200 mega Newton axial load and 800 shear displacement. The performance of this technology was verified during the 1994 Northridge earthquake in USA and 1995 Kobe earthquake in Japan, as well as the 2008 Sichuan earthquake of China. For example, a California hospital remained operational unlike other conventionally built structures in the area. Of course, even in the recent Turkey earthquake, many hospitals remained operational during and after the earthquake. So this is an example of base isolated structure. The cost of the base isolation was about 5 to 7% of the total cost. You see this bearing here, base isolator. Uh, the every base isolator in this building will extend in any direction 21 inches. And the San Francisco Airport International Terminal is the world's largest base isolated building. And Chris Chai's Church Art Gallery in New Zealand is another example. There are different types of base isolators. Normally, we encounter only bearing and elastomeric bearing and sliding bearing seismic isolator. There can be other isolators and tapping devices also, which can be used. So this is the base isolator with lead and rubber bearing. Here, the steel there is a pin made of lead, and then steel plates and rubber are alternately placed in this. And they can be either coiled springs or laminated rubber bearing pads made of alternate layers of steel and rubber and have low lateral stiffness. This is an example of this. And friction in the friction pendulum system, is found to transmit lower seismic forces into the structure compared to the lead rubber bearings, but the displacements are proportionately larger. So you can check about these systems in my paper, in my book on design of steel structures. Actually, we cannot use seismic isolation in all the cases, especially when the soil conditions are poor. We should not use. You see here, in the normal case, without isolation, this will be the point, and with isolator, it will reduce the base shear. Whereas in a soft soil condition, the base shear is amplified with isolation. So you should not use it in places such as those of the Mexican city, which is on a big lake. The major effect is increase in natural period and reduces the acceleration and thus force demand on the structure. So the forces induced by ground shaking will be much smaller than those experienced by normal buildings directly resting on the ground. So as I told, in soil survey, it tends to produce ground motions at higher periods and may amplify the response of the structure having higher periods. So it is interesting to note that BIS has released an Indian code on base isolation. There are also several codes. I have listed them here. This is the IS 1893 Part 6, and it was released in 2022. It provides guidelines for the estimation of design lateral force and displacement to be considered in the design of building with base isolation system. And according to the standards, the base isolation buildings are expected to perform better than conventional fixed base buildings during moderate to severe earthquakes. But as per this code, detailed detailing of the whole structure is necessary. Ductile detailing of the whole structure is necessary even in base isolated buildings. So we have to remember that ductile detailing is very important in any type of structure. So we will now go to energy absorbing devices. Passive energy dissipation is an emerging technology that enhances the performance of buildings by adding damping to buildings. There are different types of dampers. The viscous dampers, which consist of a piston cylinder arrangement filled with viscous silicon-based fluid, which absorbs the energy. Friction dampers, in this energy is absorbed by friction between two layers. And hysteresis dampers, energy is absorbed by yielding of metallic parts. And viscoelastic dampers containing viscoelastic material sandwiched between two steel plates which undergo shear deformation, thus dissipating energy. And other types of dampers can are tuned mass dampers. They are extra masses attached to structure by a spring dashpot system and designed to vibrate out of phase with the structure. And tuned liquid dampers, they are essentially water tanks mounted on structure and dissipate energy by splashing of water. And hydraulic activators, they are active vibration control devices and have sensor to sense the vibration and activate the activator to counter it. Required external energy. This requires external energy source and are expensive. Why should we use dampers? Dampers dramatically decrease earthquake-induced motion. There can be 50% less reduction in drift and decreased base shear up to 40%. Much lower acceleration forces due to gravity of structure. Equipment keeps working and people are not injured. So this shows the details of the viscous damper. And an example of a viscous damper used in a building. So this will be in the form of a diagonal bracing. And this is an example of the tuned mass damper, which is placed in Taipei 101 building. This is the world's second tallest skyscraper. This tuned mass damper is 18 feet diameter, that is 5.5 meter diameter, and 730 ton. It acts like a giant pendulum to counteract the building's movement, reducing sway due to wind. Of course, though it is used to reduce the wind effects, it was also found to reduce the earthquake effects. And the cost of the thing is $4 million. So, actually, we discussed about this buckling restraint brace already. BRB is a damper that was introduced by Tekita in 1976. It deals with the buckling problem of tension and compression steel braces. You may be glad to note that the original concept was developed by late engineer B.N. Sridhara of Bangalore. Several other researchers also studied and developed different configurations such as circular core, cross and crosswire core, and linear core. Between the metal joint and the concrete, this is the concept of this BRB. This is a crossed shaped thing which is inside the steel tube and which is grouted with the mortar. This method of construction allows the system to accept axial, compressive, and tensile forces which are received only by the metal link, this one, located at its core construction due to slippage. The outer mantle of the concrete is intended to limit the free bending length of the metal joint. So we will just see simple method of increasing robustness. Several committees have been formed by ACI, ERI, ACE, etc. They have disaster reconnaissance committees to study the effect of major disasters in construction worldwide and identify potential design issues requiring code change. Based on 14 different earthquakes in different countries, on the ideas of Naito in Japan and Sozen in USA, Professor Sozen has passed away. It was suggested by Pujal et al. Recently as minimum area of structural walls in RC and structural steel buildings in areas of high seismicity will prevent collapse and reduce structural damage, thereby saving lives. It could also result in increased functionality of buildings and cities after earthquake, thereby reducing population dislocation and increased community resilience. So they plotted this column index and wall index. Wall index is the smaller area of the areas of walls in two orthogonal directions plus 1/10 area of the masonry infill walls to the total floor area, and column index is the 50% of total column area divided by total floor area, plan area. They plotted this, and you see that these are the failures and these are the buildings which did not fail in the earthquakes. This figure shows more than 1,600 buildings collapse on their CA and WI ratios. Note that the buildings with severe damage are concentrated in the quadrant WI less than 0.25 and CA less than 0.37, or below the line WI equal to, that is wall index equal to 0.2%. Only nine buildings with the WI greater than 0.2 exhibited severe damage regardless of CA reinforcement detailing or shaking intensity. And separating data by the earthquake site does not change the conclusions, which is remarkable given the different areas that are considered, because the earthquakes were considered in different areas of the world. And then this shows the correlation between damage and the priority index. Priority index is wall index plus column index. So you see that in Turkey, there is a 70% damage, whereas in Chile and other places where they have more wall area, we have it is nearly equal to 0% damage. So what are the conclusions found by them, by Pujal in the recent paper in the Concrete International ACI? In the absence of rigorous field quality control and exhaustive testing, adopt structural walls areas as below. 0.2 into n of the area in each direction of the building, in buildings having less than 15 stories, where n is equal to number of floors. So detailing is critical to safeguard against large ground motion intensity and drift demands. It is better to lower drift demands, as I told you, as deformation drift can damage partitions, facades, and finishes. It will also result in increased functionality of buildings and cities after earthquake, thereby reducing population dislocation and increasing community resilience. In taller buildings, they found that wall density of 3% of the floor area in each direction is sufficient. This has been adopted in Chile already, and you may note that IS 1883-216 also says that 2% of the wall area should be provided, wall index should be provided for RC frame building with open stories. This it says only for open stories, but they found that in all buildings, if you adopt 2 to 3%, you will have robustness. So an interesting example of the robust building, um, it is a skyscraper in downtown Mexico City, Mexico, built during 1956 with a height of 188 meters and 44 stories, and it was designed by Leonardo and Zewart, and Professor Nathan M. Newmark, late Nathan Newmark of the University of Illinois, was the main consultant. It withstood 7.9 Richter scale earthquake in 1957 and also 8.1 Richter scale earthquake in September 1885. Actually, the people in this building saw all the buildings collapsing around this building. Non-structural components are also important, and not much importance was given till recently. But I think in the IS 1893 and other codes, they have given importance to that. That is cladding, interior finishes, mechanical and electrical plumbing systems, stairs, elevators, etc. They should be properly detailed and designed. It is because the cost of structural system ranges from 8 to 20% only, but the non-structural systems may be 80% of the budget. So we will go to the foundation of tall buildings, where bedrock is encountered at reasonable depth. It is better to transfer the loads through piles and caissons. Tall buildings transfer large magnitudes of load to the ground, and hence strong foundations are necessary for such buildings. In softer soil, where bedrock is not available at reasonable depth, a raft foundation is better. In many cases, piles and caissons are combined with rafts, that is, for piled raft, to increase the foundation capacity or to distribute the loads more uniformly to the piles or caissons. Special attention is to be paid to soils that have low shear wave velocity, low internal damping, and an abnormally extended range of linear behavior. They produce unusual seismic site amplification and soil structure interaction effects. You see that in the 1985 Mexico City earthquake, as I told, it is on a lake bed. Um, and it vibrated for approximately 90 seconds. A long natural period of around 2 seconds resulted in 6 and 20-story buildings to resonate and collapse. Taller buildings, whereas, suffered little damage. This shows two examples of collapse due to liquefaction, foundation weakening due to soil liquefaction in Turkey during Richter 7.4 earthquake in 1999, and shows the Nikita earthquake in Japan in 1964 during 7.5 earthquake. How to prevent liquefaction? In sandy and silty soils, if water table is near foundation level, install drainage to lower groundwater table and remove pore water. Place a porous overburden over the site to produce over consolidation. If there are no adjacent structures, use vibroplotation techniques to pre-consolidate the soil. Actually, if there are adjacent buildings, if you use these techniques, the adjacent buildings will be damaged. Employ soil grouting or chemical injection to increase the shear strength of the soil. Remove all deleterious soil and replace it with better soil. Use pile foundation to restructure on a sound strata. These are the points to prevent liquefaction. And now we will go to wind-induced failures. You see that this is a failure due to hurricanes or cyclones. The entire place is devastated. This shows the Fort Myers Beach, Florida, during the Ian hurricane on September 20, 2022, and the damages were about $55 billion. And this shows the another hurricane failure in Fort Myers, Florida, following Hurricane Ian. Professor Bruno has tracked the age of the homes, and he found that 18 homes built before 1981 are completely collapsed, but one house built in 2020 appears to be almost unscattered. The home is elevated above much of the storm surge level, but the roof also looked undamaged. So that shows that the current codes are better in resisting the damage due to hurricanes. So once again, another example which is unaffected during the Hurricane Michelle Category 5 storm that hit the Florida Panhandle in 2018, causing 74 deaths and 25.4 billion in damages. Another example of a resilient home. You see, this structure is there. This is an example of Hurricane Ike on September 2008 in Texas. So, what are the mitigation of wind-induced vibration of tall buildings? The cross section can be improved to have better aerodynamic response. The square shape is not good, but reduced corner is better for resisting wind, or having an opening, slotted corner, and so on. These are the different square cross section shapes which can be improved to have better wind response. Of course, many tall buildings are having different shapes like this. And wind tunnel testing is very important for finding out the wind loads acting on structures. So the first wind tunnel testing of a multi-story building was of World Trade Center, New York, which was built in 1973. Well, all of you know that it was damaged due to terror attack in 2001. It was tested in turbulent boundary layer flow wind tunnel in the mid 60s. These are the two towers, and these are surrounding buildings are also modeled in the wind tunnel test. Actually, during wind tunnel testing, detailed measures of pressures and sections in exterior surface of buildings are made using a rigid models. For typical building tests, large scale uh, in the order of 1 is to 300 or 1 is to 500 are used, and velocity scale is 1 is to 3 is 1 is to 5. Time scale is of the order of 1 is to 100. For example, 36 seconds in model scale represents about an hour in full scale. The results are used to predict pressures and suctions for various return periods. They are used in the design of claddings. For tall buildings, it would be normal to include a radius of at least 365 meters around the building, although 488 meters is more common. So, this is the shape of the tower in the world's tallest building, current tallest building, Burj Khalifa. In this system, each wing with its own high-performance concrete corridor walls and perimeter column buttresses the other via a six-sided central core or hexagonal hub. This results in a tower that is extremely stiff laterally and torsionally. Of course, this kind of system is used also in the 1 kilometer tall Jeddah Tower, which is under construction, which is 1 kilometer high. So in the elevation also, we can have some modifications so that the wind effect is reduced. Aerodynamic modifications are done to avoid formation of vortices behind the building through modification in elevation or through openings also. Of course, the mitigation of wind-induced vibration is through passive or approach or active approach. So this is a figure which I have taken from this uh, reference. So this shows what are the different things that can be used. That is steel damper, lead damper, friction damper, etc., etc. So let us see some examples here. The control systems can be passive, active, or semi-active, or even hybrid. And these are some of the examples of these dampers: the metallic dampers, friction damper, and viscoelastic damper. And we can have active or passive control of wind-induced vibration. The active control system can mitigate the wind-induced vibration of tall buildings by adjusting the structural damping or stiffness with a hydraulic or electromechanical actuator system. However, the drawbacks are large consumption of energy. Another various types of among various types of dampers, tuned mass dampers. Of course, I have already shown you of the Type I building, which is having the tuned mass dampers. There is a spring mass damper system that resonates out of phase with the structural motion. Then we will just go through some other disasters. So this is a recent Palisades fire in Los Angeles, which happened from January 7th to 31st of this year. This is the most destructive fire in Los Angeles history. It burnt an area of 23,713 plus 14,117 plus 719 acres, 156 kilometer square area, 24 dead and 12,000 structures destroyed, and more than 1 lakh people under mandatory evacuation, with another 89,000 under evacuation warnings. So you see that this building, as I have shown some buildings during wind damage. This ultra sturdy architecture, which includes a fireproof roof, stucco and stone walls, and piles sunk 15 meters into bedrock to withstand the uh, It was it was intended to survive during earthquake, but it stands erect amid 2025 Los Angeles fires. Whereas you see all the other structures around it are affected. Of course, this is the most popular example of a fire in tall buildings. The two World Trade Center buildings were on fire after it were struck by United Airlines Flight 175 on September 11, 2001. A reasonable fire safety should include a means to detect the presence of fire, a means to notify the occupants and fire departments of the fire, and protected pathways for occupants to exit the building or reach an area of rescue assistance. A means to control the spread of the fire is very important. It is relatively easier to extinguish fires up to 10 to 15 floors because we have standard fire equipment only with such height. Many fires in tall buildings are due to cladding materials. Actually, in Dubai, I think during which year I forgot, New Year Day, the entire building was affected by fire due to the aluminum composite panel cladding material, which has a polyethylene core and which is highly inflammable. In India also, there are so many examples of fire accidents. I have given some examples here. Lotus Park building in Mumbai in 2014, Abhar Cinema in 1987, etc. These tragedies caused substantial loss of life and property and also revealed flaws in the fire safety framework. The fire and life safety measures are stipulated in Part 4 of the NBC. They have to be followed strictly. Actually, NBC have released recently two big volumes which you can download. Although fire engineering design of RC building is possible, minimum member thickness and cover specified in codes are sufficient for most typical design fire scenarios in RC buildings. This shows the protective measures in a steel building. Steel will not burn, but it may cause soft and weak when exposed to intense heat. Building codes regulate the need for fireproofing and its required location. There are several methods for fireproofing. The method shown here are spray-on fireproofing. Spray-on material may be Portland cement or a gypsum-based product that is applied directly to structural steel members using some machines. Of course, drones can be used for firefighting. As I told you, with ordinary firefighting equipment, you can reach up to a few floors, but drones can be uh, used for at a higher heights also. So drones that travel up to 50 mph have hit the market. Their startup times can be as low as 40 seconds. Within 40 seconds, they can fly and then uh, blow water onto the structure. So flood resistant design is very important, especially in this um, period because of heavy rains coming in so many parts of the world. I am showing only one slide. So more details may be found in AIC 24, flood resistant design and construction. We need urgently in India also a document similar to this, and it is usually better to elevate the floor level and then build with flood resistant material, applied waterproofing coatings, sealants, etc., installed flood proof doors and windows, and construct permanent barriers. Examples are Netherlands Delta Works and New Orleans Levee systems. They are designed to protect against flooding. So I am giving only one example for flood resistant design, but you can refer to ACE 2024 for more details. And I think we will go to the terrorist attack. This is also a man-made uh, disaster. This shows the Alfred P. Murrah Federal Building in Oklahoma. So you see the kind of destruction due to the bomb attack. On April 19, 1985, at 9 a.m., a truck loaded with powerful bomb in front of this building exploded. 168 people died. A third of the building was reduced to rubble, and 300 nearby buildings were also affected. Preventing such collapses involved combination of structural design, construction practices, and security measures to improve the resilience. Of course, well, this is also a terrorist attack, but I have already discussed about this building. So, what are the structural design principles to mitigate progressive collapse? Increase redundancy, increase ductility, increase robustness, provide continuity reinforcement, do progressive collapse analysis. That is, if one column is collapsed, how the structure behaves, and provide reinforcement in such a way that the building will not collapse. And there are some protective measures that have been developed and used nowadays in multi-story buildings or even in buildings which are important. That is standoff distance, perimeter protection, access control. That is implement strict security measures such as ID checks, metal detectors, and surveillance systems, and blast shields and protective glazing. Use laminated and blast-resistant glass for windows and doors. So finally, I would like to stress that proper maintenance is also important. This shows the failure during midnight of Champlain Towers in Miami. It was built in 1981. This 13th floor flat slab building collapsed suddenly on June 24, 2021 during nighttime and after 40 years, killing 98 people. Official cause of the failure is not yet known. I think it has come, but I don't have the document. But however, corrosion or rebar due to improper maintenance, punching a flat slab due to this, and column failure due to corrosion may be the causes of the failure of the structure. This is the final slide of my presentation. Smart building technologies and adaptive materials can also be used. They incorporate smart building technologies such as sensors, monitoring systems, and automated response systems to detect and respond to potential disasters. Some structures incorporate adaptive materials that can respond to changing environmental conditions, such as self-healing concrete or shape memory alloys. Shape memory alloys, example one such example is nickel titanium alloy or advanced material which has the property to return to a predefined shape after deformation when exposed to heat or stress. Their super elastic and shape memory effects make them highly beneficial for earthquake resistant and durable reinforced concrete structures, but they are very expensive and a lot of research is going on in this area. So after that research, probably we can use these materials extensively. In summary, progressive collapse provisions were introduced in British and other courts as a result of the Ronan Point collapse in 1968. Buildings with regular configurations and symmetric shapes without irregularities are better in seismic zones. Of course, not only in seismic zone but also in wind zones. As per seismic design philosophy in codes, only a percentage of the earthquake growth is considered using the response reduction factor. Hence, during strong earthquakes, the structure may be damaged but will not collapse. AASC 35822 gives details and design of several pre-qualified connections, which will result in better performance. We discuss about one or two pre-qualified connections. A resilient design is required for the functioning of the structures after earthquake without much damage. Examples of resilient buildings are those which incorporate special connection detailing, supplemental energy dissipation devices, rocking systems, and base isolation techniques. Some of these we saw some of these techniques, which include structural fuses, innovative dissipative steel plate connectors, sliding hinge joints, etc. So as I already informed, extra cost is 1 is to 3% for in base isolated resilient buildings. Sorry, in non-base isolated buildings, and 5 to 7% in base isolated buildings. Robust buildings or rigid buildings have a natural period less than 0.1 second, which may not be affected much during to natural disasters. Structural walls with about 2% area in buildings less than 15 floors and 3% in buildings greater than 15 stories were found to be robust. This is based on the uh, 15,000 collapses in different areas of the world. Some authors also suggest S by T ratio to be 45. Base isolation allows isolation of buildings from earthquake ground motion. Various types of base isolators have been developed. IS 1893 Part 6 provides guidelines for base isolated buildings, and energy absorption devices can be used to mitigate the effects of winds also. We should also consider non-structural systems such as cladding because they also have impact on post-earthquake recovery. I think with this I finish the presentation. Thank you for your patient hearing.